Swayam Prabha. Digital India. Educated India.
Now, let us understand what radius of curvature is first. Okay. Next, what we are trying to do is we are trying to understand what is the meaning of radius of curvature. Curvature R. Okay. Now, say I have a curve like this. Okay. Now, what we are interested is we are interested in finding at a given point what is the circle, what is the radius of the circle R such that locally it will coincide with the curve at that point. Okay. The radius of circle whose curvature would be same as the curvature of the curve at that point locally. Okay. So, R from analytical geometry is given by 1 plus d delta y by dx whole square whole power 3 by 2 divided by d square delta by dx square. Okay. Where delta y is the curve, the equation of the curve as a function of x. This is x which deformed into like that, delta y is the equation of the curve. Okay. So, now what happens? We approximated theta tan theta which was d delta y by dx as being approximately equal to theta, because we assumed d delta y by dx to be small or of order 10 power minus 3 or lesser. Okay. Hence, what we can do is compared to 1 here, this d delta y by dx whole square will be small. So, I can approximate this as 1 by d square delta y by dx square. Okay. Now, rewriting this, then this equation becomes E by R. Okay, that is the bending equation. So, if I take a wire and wound it around this pen, the radius of curvature of that wire would be the radius of this pen at that actual location. Okay. The radius of curvature of the pen, radius of curvature of the wound wire which is bent around this pen would be the radius of this pen locally. Okay. So, I will use that radius of curvature here to estimate what my bending stresses are directly in that case. Okay. So, basically this is E by R. Now, there is one more quantity called as curvature, which is denoted by phi, which is nothing but 1 by R, okay, which is m by E I z z, which is nothing but epsilon x x by y minus y naught. That is, if you measure the strain at a particular location, the actual strain at a particular location, and divide it by the distance from the neutral axis, that will give you a measure of curvature. Okay. That is, if I have a cross section like this of a beam and I am measuring the strain, the actual strain at this location, I am measuring epsilon x x at this location, and if this location from the neutral axis is at a distance h by 2, then curvature is given by the strain at h by 2 divided by h by 2. Okay. So, that is a measure of curvature of the beam. Okay. In other words, that will be nothing but the moment, bending moment divided by E times I z z. Okay. So, to summarize, what I have seen in today's lecture is two things. We have found the bending equation for the stresses. The bending equation is given by minus sigma y minus y naught equal to mz by izz equal to E by r equal to E phi equal to E d square delta by dx square delta y. Okay. So, and then we have two more governing equations dmz by dx plus vy equal to 0 and dvy by dx plus qy equal to 0. Okay. So, now these equations govern the stress, displacement, bending moment and shear force developed in a beam. Okay. Now, how do you apply this for a given loading q of y? For a given loading q of y, the input known quantity is q of y as a function of x is a known quantity. Okay. Now, you take this and then you substitute, you will get by substituting for Vy in here, you get d square m z by dx square plus is equal to qy. Okay. You integrate this, integrate to get m of x, mz of x along with boundary conditions. Okay. Once you get mz of x, you go to the first equation, you go to this equation and what you do is you get the stress as mz of x divided by izz into y minus y naught with a negative sign, that gives you sigma xx stress, that gives you sigma xx stress. Okay. Then you use the final equation to get d square delta y by dx square to be given by mz divided by E times I z z of x. Okay. Now, you integrate this, integrate to get delta y along with the boundary conditions. Okay. Now, combining these two equations, what I get is I get d square by dx square to E times I z z d square delta y by dx square equal to q y. Okay. So, this is the governing equation for displacement of a beam. Okay. That is the Gaudin equation for the displacement of the beam. Your finite element codes like SAP, ETABS, Abacus, ANSYS, all these solve this equation to get the response of a beam. Okay. So, in the next class what we will do is we will take up specific examples and work out the details on how to solve this problem and how to get the stress, strain, your displacement, your shear force and all the response quantities for a beam. Okay. Thank you.